In this presentation, we are going to look at information theory, and in particular what we're going to do is look at information rates, okay, the average information rates. So if the time rate at which a source X emits symbols is R symbols per second, the information rate, capital R, of the source is given by the following expression there. Capital R equals small r times h of x bits per second, okay? That's the entropy. Okay, h of x is the entropy. Small r corresponds to the symbols per second. Okay, so a high resolution TV picture consists of about 2 by 10 to the 6 picture elements. Now this is important. I'm going to split this up into two and we'll read through the question twice. 2 by 10 to the 6 picture elements, which is 2 million essentially. So that's got 2 million symbols. Okay. And also it has 16 brightness levels. Now I'm going to make note of that as well, but I'm going to give it a different color, 16 brightness levels, because that's going to relate to entropy. Okay. Pictures are repeated at a rate of 32 per second. Okay, so that, again, that is the picture, the time rate. That relates to small r. All picture elements are assumed to be independent, okay, and all levels, which means brightness levels, have equal likelihood of occurrence. So I'm going to make note of that because that also tells us what the entropy is there, that part there. Okay. Calculate the average rate of information conveyed by this TV picture source. Now, this is a sort of a bit of a clue here, okay. It says the TV picture source, okay, so that means we have to combine this value and this value here, okay. So we have 2 million picture elements and each element gets refreshed at 32 per second, so overall we have 64 million symbols per second. 32 for each of the 32 per second for each of the 2 million picture elements, okay. So that's important there. That gives us our rate value for small r. Now let's calculate the entropy as well, h of x. So we're told that they're equally likely and the levels are equally likely, and so there's 16 of them. So that means we deduce that the probability is 1 over 16. Okay, so that gives it, and they're all consistent the whole way through. So pi for each one is 1 over 16. So we just put in that 1 over 16 there. So this is the expression we would use to calculate the entropy. Now it's sort of straightforward enough in this instance. It's 16 identical elements there. Each expression is minus 1 over 16 times log to the base 2 of 1 over 16. Okay. And so what we're going to do there is we have 16 identical elements, compute one and multiply it by 16. Okay. So this is one of them. That's the entropy for one of them. Minus 1 over 16 times log to the base 2 of 1 over 16. And because there's 16 of them there, just multiply that by 16. Now you can tell straight away that cancels out. So what we're left with is minus log to the base 2 of 1 over 16. That is minus times minus 4, which is 4. So the entropy is 4 bits. Okay. Small r, which we said was 64 million, okay, 2 by 10 to the 6 times 32 bits per elements per second, 64 by 10 to the 6 elements per second for this TV source. Now it's not just per element, we're doing the whole source, all of the 2 million of them, because that's what we're asked in the question up above here, okay. So multiply that out. Capital R, the average information rate, that is small r times h of x. That is 64 by 10 to the 6 by 4. By the way, I just started keeping it 10 to the 6 because that's a million, a mega. Okay, 256 times 10 to the 6 bits per second. So that's our answer there. 256 megabits per second. Okay, we'll leave it there.